Hello students, welcome to part 10 of module 2. Now in this video, we'll try and write another custom encoder which I call the insertion encoder. Now what is really the insertion encoder? So let's say this is how our original shell code looks like. In the case of an insertion encoder, I basically insert an absolute garbage byte, right, between every 2 bytes of the original shell code. So you can actually see AA in between every 2 bytes of the original shell code. Now variations of this can be, instead of AA, you could have a random value, or you could probably have an increasing sequence and things like that, right? So the basic idea is that there is garbage, and this would end up probably confusing a lot of AV and IDS systems. Now, how do we go ahead and write a decoder for this? So the idea is again similar to what we've done in previous videos, which is write an insertion decoder stub. And what that stub would do is that it would take, let's say, the next legit value of the shell code, which is AB, and then put it in this location where the first garbage value is. Then it would take the value of AC and then put it to the place where AB is. It would take the value 0, 1 and put it in AA, right? So that what is happening is the original shell code is now moving at the absolute front, and we are overwriting all the values and ensuring that no garbage value now exists in between. Once this whole process is complete, just like in previous cases, we send control to the beginning of the original decoded shell code. So let's go ahead and do this. Now I have written a very simple Python script to do the insertion encoder, and all it really does is it will take a piece of shell code and insert 0xAA after every byte of the shell code. Now in the same directory, I already have execv stack.nasm. This is exactly similar to what we've encountered in previous videos. I'm going to cut that out. So I'm going to have basically execv stack. Copy this out. Let's just quickly verify that the shell code works. Let me paste it into shellcode.c. Compile, execute, and it works perfectly, right? Shellcode length is 25. Now I'm going to take the same shellcode and paste it inside our Python script. And run the Python script. And this is going to give us the new shell code, which has 0xAA inserted in every even location. So now the length of this shell code is actually 50, right? Because the original shell code length was 25. Now let me actually write the whole decoder program. So let me call it insertion decoder dot. Let me actually copy out the template just like I do for every other video. It's just easier to work that way. Template.nasm, and let's call it insertion decoder.nasm. Open it up. Insertion decoder.nasm. Let me remove all of this stuff in here real quick. And here we go. Now I'm going to paste the modified shell code with the 0xAA encoded in it. So let me call it, let's say, what do I call this? Encoded shell code. And then let me paste it. There we go. And now let me go back to writing the decoder. Now, just like what we've done before, I'll get the encoded shellcode address using the jump call pop technique. So we have jump short call shellcode, and here is the call shellcode label. Here is the actual call statement, which is going to call the decoder. Here is the decoder, and of course the only thing I need to quickly do is pop ESI to get the address of encoded shellcode, and here I'm going to type in my decode routine. Now, what is it that we want to do? We basically want to take every odd value, which is we want to take this and replace AA with this value, and then we want to take 50 and put it in the location where C0 is. Then we want to take 68 over here and put it in this location AA, right? So of course we would need a counter which slowly increments and allows us to do that. However, we would need two counters. One is to keep track of the next AA and the next value of the real shellcode byte, and the other would be something which incrementally moves along this path to ensure that we actually get back our original shellcode as one packed structure, right? So let me use EDI as the other counter which slowly tracks along the encoded shellcode length. So let me say LEA EDI, and I'm basically going to have ESI plus 1, right? So ESI plus 1 really is tracking the 0xAA at this point, right? Because ESI is pointing to 31 at this point. Now let me quickly initialize a little counter XOR EAX, and I'm going to move the value 1 inside EAX. I'm also going to generate XOR EPX. Right, there we go. Now what I'm really going to do is the following: move BL byte ESI plus EAX. Now what does this do? ESI currently is pointing here. EAX has the value 1 inside it. So basically ESI plus EAX is pointing to the very first AA. Now what I really want to do is I need a method by which I can also figure out when I should stop decoding this shellcode, right? Because we can't just move indefinitely forward, and God forbid there are tons of AAs there just to confuse us in the rest of the program memory. So how do we go ahead and do this? Let me show you how. Now what I'm about to do is basically at the very end of this shellcode in here, I'm going to put in two values, 0xbb, 0xbb, and I'll just explain in a bit what these are going to do. Now in the next instruction, I'm going to basically do a XOR between BL and 0xAA. Now please note that till the time we are in the context of the legitimate shellcode, this would end up resulting in a 0, and hence the 0 flag would be set. Now after we end up going beyond the legitimate shellcode, we would end up XORing with BB, and this would end up with a non-zero value. So what this would mean is that we have ended our encoded shellcode, which means we can now comfortably go to executing the decoded shellcode, right? Which is exactly beginning from the same location. So I could very easily just do a JNZ short encoded shellcode, right? Now, till the point this does not happen, what that really means is that we are still continuing along the length, and we need to transfer the next value to the location where the next available original shell code needs to be inserted, right? So how do we do that? Well, very simply, what I'm going to do is move BL, and then I'm going to have byte ESI plus EAX plus 1, right? Now in this context, what I'm really doing is I'm picking the value C0 up and putting it inside BL. And as you probably imagine, the next step would actually be to store it using EDI. So the next step would be move byte EDI and basically from BL. For a second, let me just tell you what just happened, right? EDI is actually pointing to the next value as pointed to by ESI. ESI points here, which means EDI is pointing here. Now what this instruction has done is it's taken the value C0, put it inside BL, and in the next instruction it is copying C0 to the location pointed by EDI, which is this location. So C0 basically got shifted here, right? So now in memory it's 31 C0, right? Fantastic. Now after this, as you can imagine, we would have to increment EDI so that now EDI points to this location, which is where C0 is currently shown in the figure. So I'm going to do an increment EDI. And of course, because the 0xAA is at every even position, we would now need to increment EAX by 2. So I can just do an add AL2, right? And this needs to continue in a loop. So I'm just going to do a jump short decode, right? So this would again go back in here, and this would continue to happen till the time we do not hit an AA at the even location. And when that happens, immediately we know that we have finished our decoding and transfer goes to here where our shellcode executes, right? Hopefully everything is okay. Let me go ahead and run this. Looks like one small error somewhere. 14. So you not have this. Let's go back in here. Everything assembles fine. Let's use object dump to quickly check we don't have any nulls. Right, we don't have any nulls. Let's cut out the shellcode. Copy this in. Let me open shellcode.c. Compile, and let me now run this. And awesome, if you notice, now we have our bin sh shell just as expected. Let's quickly actually look at GDB and see what was really going on in all of that decoding, right? Okay, here is where we are. And our encoded shell code, if you can quickly recall, starts from basically this location, right? Just below the call, right? So what we really want to do is that we basically want to look at how this is changing over time, right, in each single iteration. So let's go ahead and basically do the following. I'm first going to ensure that we are looking at the shell code. So let's say X can do a 20xb, add this address. Okay, and now if I were to look at my file, which is shellcat insertion decoder.nasm, you would notice that it's 31 AAC0 blah blah blah, which is exactly what this is, right? So the first thing I'm going to do is also set up a breakpoint in there so that, you know, as soon as the decoding finishes, we know that things are going on fine and we can see the decoded shellcode. And now I can just quickly step through the instruction set to see how the shifting is happening, right? So let me go ahead and do the following. Let me quickly just do a couple of step eyes. Define hook stop, disassemble, alright. So let me kind of go ahead and run this a couple of times. If you notice right now, basically the insertion encoded shellcode is just as is, simply because we haven't entered the loop in there. Let me hit enter a bunch of times so that we are in there inside the loop. Right, now this is the first place where the move is going to happen, and right now nothing has happened, but you will notice that just after this instruction, C0 would actually be shifted to this location, overwriting this A. Awesome. Do you notice C0 overwrote it? Now the next time this runs, basically 50 would end up overwriting this location in here. So let's go through this real fast, right? That is actually a simpler way to do it. I'm just being stupid here. I could basically just do a breakpoint at this location. Right, so I'm going to have a break star, paste, and let me continue. There you go. And if you look at this, 50 overwrote it. The next time this runs, basically 68 would override this AA. There you go. And now 2F would end up overwriting 50. There you go. And now again another 2F would end up overwriting this AA in here. There you go. Now while this is happening, if I quickly disassemble this location, you would actually notice that your original shellcode is kind of slowly starting to come through, right? Let me paste this in here. Do you notice that? We see our little push, our XOR EAX and push EAX and all of that. And if you remember, this is really nothing but execv stack.nasm kind of slowly coming out, right? Here it is. Here is the next value. That's slowly happening, right? Continue. And this would keep on happening, of course, as we keep moving the original shellcode back into its logical position. Now, what I'm going to do is basically we could just go ahead and continue and see all of this happen, right? And I could just quickly kind of see that the whole shellcode would be transferred in this way, as you can clearly see. There you go. Now breakpoint 2 was hit, and we basically have our shell in place, and all the disassembly has happened, right? And I just wanted to save for the last one, but fortunately it couldn't happen. So let me quickly rerun this. No problem. I'll just set up everything quickly once again. Set a breakpoint for code, run, disassemble, set up our breakpoint just after the call instruction in here, which is basically this location, so that after the whole decoding can happen, we can see that we have our original shell code back. Continue, disassemble, and here we are, right? If you notice, this is exactly nothing but the execve stack.nasm shell code, and all of that has now been finally decoded by our insertion decoder, and we continue execution. Awesome. So hopefully this example was crystal clear. In reality, guys, what I'm really trying to tell you is use your creativity and imagination, right? As I said, writing a custom encoder is really you creatively envisioning how you would want to shift things around, or encrypt things or encode things, and it isn't very difficult if really you want to use this for your own personal purposes. Now the difficult part, as I mentioned, would be if you want to make this open for everybody's use, then it's going to be basically a cat and mouse game between you and the AV and IDS manufacturers, right? Okay, awesome. Try this out. Try out variations. Think about what would happen if instead of AA we inserted random values. In that case, would you use the length, or could you use something else, some other marker through which you could know when your shell code ends, so that you can move along with the execution? Think about it. Write a couple of snippets yourself to gain more confidence. So that's all I have in mind for this video. Thank you.